Thank you for coming. My name is Ayin Vala. I'm the co-founder and chief data scientist at Foundation for Precision Medicine. We are a nonprofit at the intersection of AI and medical science. And we have two main initiatives, one in early detection of Alzheimer's disease and one in studying opioid epidemic. Again, we're a nonprofit, and the work I'm going to show today is a collaborative effort with Stanford University. We work with their computer science department and biomedical data science department. Google is our partner for cloud computing, and Mayo Clinic and Yale School of Medicine for medical expertise and medical direction. So before that, I'm going to show a little video just to give you a little bit of a taste of what we're doing. Disclaimer, this is the work we did with Google Cloud. So there are some talks about Google Cloud. It's only 2 minutes long. But, you know, AWS, Microsoft, Intel, Oracle, they all have great tools.
My name is Robert Tabbs, and 5.5 years ago, my mother was diagnosed with Alzheimer's. I knew none of the medications were working. The entire time was a downward spiral.
And I also lost my grandfather about 25 years ago to the disease. My family at the time felt like it was already too late to change the trajectory of the disease. And it breaks my heart when I hear the same stories today. The mission for Foundation for Precision Medicine is to bring AI and healthcare together to detect Alzheimer's early.
If you can detect Alzheimer's very early on, that is when the disease is most susceptible to treatment.
The data that we have access to are anonymized electronic healthcare records. We needed a HIPAA-compliant environment, which is why we use Google Cloud.
We're dealing with hundreds of variables on millions of patients, which generate billions of lines of data.
Google Cloud enables us to scale our operations, and with BigQuery ML, we're able to develop machine learning models faster and utilize our entire data. Being a nonprofit, we rely on our volunteers across the US, and Google Cloud really enabled us to do that. We wanted them to be able to apply machine learning on the data and look at trends themselves to empower them to come up with more innovative approaches to change the progression of the disease.
This work is so important to me because it helps us address this devastating illness that has no cure.
I heard somewhere that they said, don't forget that dots on the plot are people. And we really take that seriously.
Thank you for watching that. Just to get a gauge of audience, when I say EMR, who thinks Amazon's Elastic MapReduce? Who thinks electronic medical records? All right, so mostly healthcare audience. That's great. The point of the talk is really we need people that know both of those, not just one. All right, so as you saw in the video, currently there's no treatment or cure to prevent Alzheimer's disease. There's some treatment that lessen the symptoms, but there's no real cure. And it has become a huge problem. This is changes in death rate in the past 20 years. So when you compare how many people die today compared to 20 years ago, for example, HIV people die 50% less now than they did back then. But for Alzheimer's disease, it has become more than doubled in 20 years. Some of it is because we don't have good treatment. Some of it is because people now live longer. But there are also other contributing factors. So it has become a huge problem. It's the 6th leading cause of death in U.S. And it's the most expensive single disease that we have. It takes away 1/4 of our healthcare budget, the entire healthcare budget. It's about $1 trillion. This takes away $260 billion. That comes mostly from taxpayer money. So it's a staggering number. And also 2 in 3 are women. One contributing factor is women live longer, but the other contributing factors is still in debate, and there's a lot of research that's been going on right now. It's not all bad news. Drug companies like Eli Lilly, Genentech, Pfizer, they all have drugs, and they tried drugs for Alzheimer's, and they didn't have really good luck. But in the past couple of years, for example, Eli Lilly came out and said, the drug failed in a clinical trial, but it showed good results for a subpopulation of those people, the people who had early onset of Alzheimer's and or maybe they had mild dementia. Their drug actually showed good results for them. So now researchers they believe that early detection is the is the key to preventing slowing the disease and hopefully at some point curing the disease in future. And when you see early detection, and we are in the a data science conference, we think predicting what is going to happen based on historical data points. So this is very a difficult problem, very challenging problem, and one of the biggest challenges for us was to sort of frame this into and massage it into a data science problem and see how we can attack this problem from a different angle. There are clinical trials going on, drug discovery is going on, the clinical research has been going on, but what can we help with AI in this for this disease? So going forward, what we saw right away was, to be able to reinvent healthcare and move forward, looking in this Venn diagram, you really need all those three to be able to do, make a big impact. For example, big corporations now, they have data scientists, they have organizations for data science. They work with large hospital systems, they can get clinical data, but it's hard for them to really gauge intimately with medical experts in clinical research. Medical institutes, for example, research hospitals like Stanford School of Medicine, they have medical experts on staff. They do have access to very good quality clinical data, but it's hard for them to work with computer scientists and data scientists, even though they may be one building down the road. So really adding those three is what we really try to do from the get-go. And again, we're a nonprofit. So we went, in the beginning, we went around and tried to get our hands on as much data that we can. We were a nonprofit. It made it easier for us to do that. If you're for-profit, when you're going to get healthcare data, a lot of questions come up and they say, well, if you're going to make a tool based on this, what is it in for me? And those kind of stuff. But as a nonprofit, it was easier for us to do that. The biggest challenge here in healthcare, and everybody knows this, but the biggest challenge is data is in different silos, so they're not really connected. So that's part of the big challenge that we had. I'm going to talk about two studies that we have done today. Based on those two data sets, we have a large electronic healthcare record, mostly structured data for 4 million patient records from about 40 states in the U.S., and 100,000 of them are flagged as Alzheimer's, and these are diagnosed patients in a facility setting from a doctor. So that's for a binary classification, that's what it is. Another data set that we have is 2,000 brain MRI scans from 2,000 patients. Actually, it's more than 2,000 MRI scans, but it's 2,000 patients, and half of them were diagnosed with Alzheimer's and another half were healthy. So we'll show some preliminary work that we've done with that also. And our goal was to alter the course of progression of Alzheimer's for these patients. First thing that we had to do was to collaborate with clinical researchers and understand the domain knowledge at least a little bit. And then we wanted to do early detection with structured data, also look at MRI images and see if we can do anything with that. And if possible, implement it into an app or implement it into a decision support tool, just like anybody else is trying to do in healthcare. And those were our goals. So first thing that we did, we went and curated hundreds of papers in Alzheimer's in the past 20 years. We got them all, we looked at them, and we tried to see what are the general trends that we see in these papers, and what are the variables that the clinical researchers are looking at, and maybe they determine some kind of factor based on a small clinical trial that they did, and see what are the factors that they were looking, and can we extract those from our data for each patient and use those as features and variables to be able to predict the onset of Alzheimer's. So, give you an example. For example, diabetes is very correlated to Alzheimer's, and they said you have a greater chance of Alzheimer's if you have diabetes, and some of these things are correlations. Sometimes it's causal. Maybe in case of diabetes, maybe it's causal because blood sugar gets mixed up in the body, and then and brain needs glucose all the time. So maybe that causes some adverse effect. When it comes to cardiovascular disease, blood flow to the brain decreases, so maybe that's why neurons die quicker. So those are the things that we try to extract from historical diagnosis for each patient and use it as dependent variables, predictors, features, whatever you want to call them. And sort of the vision that we had was, you have structured data that comes in from electronic health records. You can throw it into a machine learning model, get some prediction there. Then maybe you have the MRI image for the person. You throw it into your convolutional neural net, however you want to do it. And maybe you have doctor's notes, and you can do word embedding and get a prediction from there. And maybe after combining all those together, you can get a good, accurate assessment for a patient. I will talk about the first two today. And again, the challenge is the data we have is from different set of patients. So we're not able to do this right now, but as we figure out how these EMR records are going to work in the next 5 to 10 years, we'll be able to do this, hopefully get a whole picture for a patient. We're working with Stanford, and Stanford has this data set. They call it a Danish data set. What's interesting about that data set is they have the whole picture for each patient. So it's very interesting work and research. So early detection with structured data. What we did, we extracted those features that I told you, age, gender, encounter data is sort of a data that you get when you go to a facility. Comorbidities is like those chronic conditions that I talked to you about, diabetes, cardiovascular disease, hypertension. Some eye diseases are correlated to Alzheimer's, and we're able to extract those based on historical diagnosis for each patient. Medications also, we took those out. We know who took what and when they took it. There are some medications out there, for example, some sleep disorder medications that have shown may have adverse effect to Alzheimer's. So we use those also as variables to see if they're significant or not. Throw it into an algorithm. You want to start with simpler algorithms like logistic regression, because you can explain it to somebody in a clinical setting. But we work our way up to deep learning, deep neural nets, and the model that we're using now is actually a stack ensemble model that combines all these models together. And what we're trying to do is to predict the chances of Alzheimer's for each patient, sort of in a low, medium, high setting. So that's a prediction, but also wanted to know like the contributing factors. So that's more of an inference aspect of the work. We want to know, what are the biggest contributing factors generally in entire population, in subpopulation, personalized to a patient. And that kind of inference is actually more important and more interesting to clinical researchers. That's what they're interested in. And right now our models, it's between 0.8 to 0.5 area under curve is the accuracy that we're getting. That's pretty good. That shows that we're able to, understand a signal, from noise. We're doing more work to get better algorithms. The tools that we use, again, we heavily use a Google Cloud environment. All of our data is up there. They have a HIPAA compliant place that, we were able to actually put our data up there. We use BigQuery to query large amount of data. You can query billions of records in a matter of seconds. It's crazy how good it is. And it's Amazon has Amazon Redshift, which is like Google BigQuery. Now they have added machine learning in the same environment. You can do machine learning there. I think it's in beta version now. Data Studio, our clinicians like that. It's sort of like a Tableau online, and it's powered by BigQuery, so they can actually see billions of rows, plot it fast, so they don't have to like download it into an Excel file or something like that. It's a drag and drop way of doing it, so they're actually able to do some work themselves. And we use Data Lab. It's like Amazon SageMaker to run Python code, and our data science like Python, and we use Kubernetes engines for developing our app and using its containers. So the work that we were, this was our vision, and I worked in the aviation industry before, and this is sort of a dashboard that our pilots have had for past 4 years or so. It's very data driven, and the vision for healthcare right now is something like that for doctors. So when physicians in the office have this, many apps that they can see, and hopefully they're all connected to the EMR record and they're very user friendly and all those things. It's the goal. And this is sort of our vision to get a spot there, in front of a physician. But we found that it was very difficult to actually infiltrate in a hospital system or actually put this in front of physicians. They're very busy. They don't want to work with another tool. The hospital system, there's so much politics with that. So it was very difficult. So we were a small nonprofit with not many connections to large hospital system. So we sort of pivot to an Alzheimer's prevention app. So we thought, okay, if we can't get it in the hands of physicians, we can easily get it in the hand of patients who actually care about Alzheimer's and their chances more. So this is a mock-up that we are working on right now. It's in final stages for an actual app. So it's a free app they can download. They put their information in, their age, if they have family history of Alzheimer's, if they have one of those conditions, chronic conditions that I told you about, what are the medications that they're taking. It's totally anonymous. We're not after the data. We have enough data to worry about. And the result is sort of, medium, high, low, medium, high risk, for the patients. And also it says, recommendations of what are the medications to avoid. For example, we see that a drug called lorazepam may have adverse effects. So if the patient is taking that, we say, maybe you need to talk to your doctor. So the goal is to really have the patient go to a doctor and start the conversation with the doctor. That's where our work is done, and we are happy with that. We're not trying to replace the doctor. And by the way, in the past 4 years or so, we never replaced the pilots either, even though there's a lot of autopilot has been around since the 70s. So we're just trying to empower our doctors. So that's the work we're doing. In terms of detection with MRI images, so we had a limited amount of MRI images that we could work on from 2,000 patients. And our goal was, can we, in an automated way, be able to build an algorithm that maybe can detect the things that an expert would detect right away from looking at pictures, right? So when an expert look at an MRI image, on the left, it's a healthy brain, and on the right is Alzheimer's brain. And these are the things that they would see right away. So these enlarged ventricles at the center is, it can be telling of Alzheimer's disease. Overall shrinkage can be telling, and also shrinkage in hippocampus. This is where the memory is stored. Those are all telling. So our goal was, can we build an algorithm to be able to do that? And this is the result from our algorithm. So on the left is predicted Alzheimer's. Sometimes it's correct, sometimes it's not. The green is correct, red is wrong. And on the right is predicted not Alzheimer's. And when you look at it generally, you see that it's seeing these large ventricles as a signal, as something that's telling that this might be an Alzheimer's patient, compared to the small ones on the right. Also, the overall shrinkage, it sees that, and maybe in hippocampus and other places, it sees that as something that could be telling for Alzheimer's. So this is what we have right now, and we use PyTorch and transfer learning. If you're interested, check out transfer learning. Is it's going to be huge, I think, in the next few years. And we are achieving about 80% accuracy on a 50-50 sample, with pretty good precision and recall. The doctor, or an expert's ranges from 90% to 95% accurate. So we think with better modeling and adding much more images, we will be able to bring that up. So yeah, that's it. And we are a nonprofit. I put this out. If you're running a nonprofit or know someone, Google has this program, Data Solutions for Change. They give you cloud credit. If you're a nonprofit, the application is pretty easy. We used that at some point, and it was very beneficial to us. And again, thank you very much for coming. I'll take your questions now. Yeah, absolutely. So, you want to always bring your accuracy up. That's something we would want to do as data scientists who grew up on Kaggle competitions. But in reality, depending on your environment and what you're trying to do, especially in healthcare, precision may be much more important than recall. You don't want to send somebody home and tell them they don't have Alzheimer's or they don't have cancer and end up having cancer, So you would play with those sensitivity and specificity, and that would bring your accuracy down. That's something that we actually talk to the researchers and then talk to people who have experience doing this, trying to figure out what they do. What we are doing is just to empower patient and give them an algorithm as something to look at to start conversation with the physician. We try to have higher sensitivity, and that's something that we'll look for. In healthcare is very, very important.
So you mentioned that you use transfer learning. So what was the original
we had a few thousand images, which is not great for a deep learning algorithm, and we found out, So what? Oh yeah, the question was, you're doing transfer learning now, what were you doing before that? We built a convolutional neural net on the images that we had, and it wasn't really accurate because it didn't have as many images. So with transfer learning, you're using models that are based on, cats and dogs and change the last layers to get a better accuracy, and accuracy actually went up much higher using that. We're using, I think, Inception v3 from Google. So you should look it up, the theory behind it, but in a short amount of time, I can tell you it's sort of like when they make those very huge deep learning models, the first 70-80% of the layers are just to extract features, so extract shapes, extract edges, those kind of things, and at the very end, it gives you a set of features, set of numbers in a matrix format that is abstract representation of what the image is to the computer. And it matches that to the outcome, in this case, Alzheimer's and non-Alzheimer's. So you are using all the things before that, the getting all those shapes and everything, you don't change those things. But the last layers, you just match them to different labels that you have. It works surprisingly well, but again, if you have like millions of images for MRI images, which nobody has, it would be better if you just make a model just based on that. Yeah, absolutely. Our work really, and clinicians really don't worry about, and question, sorry. You asked what are the factors that the model is looking at, and yeah. Right. Mm-hmm. Yeah, so the question is, what are the dominant factors that your model is thinking? So that's what I was getting into. For clinical researchers, they don't care about, how much your accuracy is. They want to know the inference. They want to know what is your model thinking, what are the factors that it thinks are important, and which are less important, which are more important. Our model really right now sees a lot of comorbidities as huge factors. So diabetes, hypertension, cardiovascular disease, those come up high. Medications don't come up as high. There's some lab results that come high. And those really match what you see in the research. So I saw somewhere that they said, at some point they said diabetes bring your chances up about 30%, and now they're saying 50%. Our model actually shows 40% higher chance of Alzheimer's if you have diabetes. So we try to evaluate our work with clinicians, and it's an ongoing iteration, and they always ask really good questions, and sometimes you can answer them with data and sometimes you can't. Okay. Mm-hmm. Exactly. So we are actually publishing our work. Hopefully next month or so we submit it to NIPS. If it comes out, we'll let you know. One more question.
So for like a disease like Alzheimer's disease, where right now you don't really know what's actually causing it, there's a lot of proposed correlations, such as gene expression, amyloid beta, tau, things like that. I was just wondering, how do you see deep learning or your model helping to reduce noise data, or finding ways that can help lead to innovative strategies to help treat.
Yeah. So. Yeah, if I get a question right, I think you're asking how are you using deep learning to look into those features that others like genetics factors and that other people are seeing. How are you using for innovation? Is that what the question was?
Or just how to, I guess in your model, to help increase earlier detection of Alzheimer's disease. Because right now there's not drug trials for Alzheimer's disease like that too.
Yeah.
So I was just wondering, how can we utilize these neural networks or these large amounts of clinical records that we have to, I guess, just help with finding earlier detection, more accurate predictions.
Yeah. So we try to not just throw the data into the model and see what we get. We were very specific about what are the variables we were giving it, whether it was genetics or not, and whether it was just comorbidities, and work our way up. So what we're doing is to adding more features to our models. And first we started with just logistic regression because you actually can see the weights for each factor. You can talk to somebody with an Alzheimer's research background and see if what you're doing is correct or not. The models, the neural network models are more complex, and sometimes it's doing stuff that you can't really look inside and see what it's doing. There's also ways to sort of rank the importance of each factors. Those are the things we're looking at, that's the work that we're doing. More complex algorithms give you better accuracy, but less interpretability. Good. Thank you very much. I'll be outside if you have any more questions.